The most dangerous idea in physics right now is not about black holes. It is not about the end of the universe. It is about the second that just passed. Physicists wrote one equation to describe everything. Every galaxy, every atom, every moment you have ever lived. And when they solved it, time was missing. Then in 2025, Oxford built a clock from a single electron and discovered that reading it cost 1 billion times more energy than running it. Measuring time cost more than time itself, which means time might not be something the universe contains. Tonight we find out what that means. Stay until the end. If you are new here, welcome. Subscribe, get comfortable, and stay until the end. Because by the time this is over, the present moment, this one, right now, is going to feel like the most radical idea in all of physics. Now, let's get into it. Part 1. The claim that breaks reality. There is an equation sitting inside the foundations of modern physics that does something no equation should be able to do. It describes the entire universe, every particle, every field, every possible configuration of energy and matter across all of space. And when you look at it carefully, when you actually read what it says, time is not in it. Not approximated away, not simplified out for convenience. Gone. Completely and structurally absent, the way a building has no fourth floor not because the architect forgot, but because the design never included one to begin with. And here is why that should disturb you. You're reading this sentence right now. 1 second passed between when you started and when you finished. You felt it. Your brain registered it. Your heart beat once or twice in that interval. Your eyes moved left to right across the words, and somewhere in your nervous system a timestamp was applied. That experience of duration, that felt sense of one moment following another, is so fundamental to being alive that we almost never question whether it is real. We question a lot of things. We question whether we can trust our senses, whether our memories are accurate, whether the news is telling us the truth. But we almost never sit down and seriously ask whether the second that just passed actually happened. The Wheeler-DeWitt equation asks you to do exactly that. This equation was developed in the 1960s by physicists John Archibald Wheeler and Bryce DeWitt, and it represents one of the most ambitious things theoretical physics has ever attempted. It is what you get when you try to write a single quantum mechanical equation for the entire universe simultaneously. Not for a particle, not for a field, not for a region of space, but for the whole thing, treated as one quantum system. If quantum mechanics works everywhere, the reasoning goes, then the universe itself must obey some version of it. The Wheeler-DeWitt equation is the attempt to write that version down. The problem is what you find when you do. In standard quantum mechanics, the kind that describes electrons and photons and the behaviour of matter at tiny scales, time is a background parameter. It is the stage everything happens on. You set up your equation, you watch your quantum system evolve forward through time, and time sits there quietly doing its job, moving the story along. Time is not in question. Time is the medium. But when you try to write a quantum equation not for a system inside the universe, but for the universe itself, that background disappears. There is no stage outside the universe to stand on. There is nothing external that the universe is evolving through. The universe is everything, which means time cannot be the thing it evolves through, because there is nothing else. And so when you do the mathematics, when you actually sit down and grind through what a wave function for the entire universe looks like, time drops out. The equation you get is static. It describes a universe that does not change. A universe in which nothing happens, nothing evolves, nothing moves forward, because there is no forward to move through. Let that land for a moment. The equation that is supposed to describe everything says that nothing happens. You're sitting there, blood moving through your veins, neurons firing, the clock on your wall ticking, and the most fundamental description of the reality you inhabit says that none of that is part of the basic structure of existence. It says that the universe, at the level of its deepest mathematical description, is not a movie. It is a photograph, a single, static, unchanging configuration of everything, described by a wave function with no time variable anywhere in it. Now, you might be thinking that this is some fringe speculation, that this is the kind of thing theoretical physicists scribble on napkins at conferences and then never publish. You would be wrong. The Wheeler-DeWitt equation is not controversial in the sense of being dismissed. It is controversial in the sense that physicists take it seriously and find it deeply, structurally unsettling. It appears in textbooks. It has been cited thousands of times. It is the central object of study in a field called quantum cosmology. And the discomfort it produces is not the discomfort of a bad idea. It is the discomfort of an idea that might be right. Here is what makes this especially sharp. The equation does not emerge from a philosophical preference. Nobody decided time was probably not real, and then worked backward to find supporting equations. The Wheeler-DeWitt equation is what you get when you do something completely pragmatic and scientifically motivated. You take general relativity, which is Einstein's theory of gravity and space-time, and you try to combine it with quantum mechanics, which is our best theory of matter and energy at small scales. These are the two greatest physical theories ever constructed. Together they account for essentially every phenomenon we can observe or measure. And when you try to unify them, when you try to write a single framework that includes both, time vanishes from the result. General relativity treats time as a dimension of geometry. Space and time are the same thing, space-time, and gravity is what happens when that geometry curves. Time is flexible, stretchable, relative to the observer. It is not a universal clock. Two observers moving differently or sitting at different gravitational potentials will measure different amounts of time passing between the same two events. Time is physical. It bends. It stretches. It is part of the fabric. Quantum mechanics does something completely different. It treats time as an external parameter, a fixed background variable that ticks along reliably while quantum states evolve through it. Quantum mechanics does not curve time. It does not question time. It uses time. And when you try to build a theory that respects both frameworks simultaneously, these two incompatible treatments of time collide with each other, and the mathematics resolves the contradiction by eliminating time entirely. This is not ignoring the problem. This is what solving it looks like. And so what we have right now, sitting in the literature of physics, is the possibility that the most fundamental description of reality is a description of something static, that the universe does not happen, that it does not evolve, that it simply is, all of it, everywhere, always, in a way that contains no moment called now, no direction called future, and no region called the past. And yet here you are, 1 second after the last, already wondering what comes next. Part 2, not a theory, a mathematical result. It is worth being precise about something here, because the natural response to what was just described is to treat it as a theoretical preference, as one school of thought among many, the kind of thing where some physicists believe it and others do not, and you can pick a side based on your philosophical leanings. That is not what this is. The disappearance of time from the Wheeler-DeWitt equation is not a belief. It is a result. It follows from the mathematics the same way a sum follows from arithmetic. You put in the inputs, you follow the rules. Time is absent in the output. That is all there is to it. To understand why, you need to sit with the tension between the two theories being unified. General relativity at its foundation treats the geometry of space-time as a dynamic physical object. The shape of space-time changes depending on what is in it. Mass curves it, energy curves it, and those curves are what we experience as gravity. In this framework, there is no fixed background, no pre-existing stage on which events play out. The stage itself is part of the physics. When physicists say that time is flexible in relativity, they mean it literally. Time is a part of the geometric structure of the universe, and that structure responds to physical content. quantum mechanics treats the situation completely differently. In the standard formulation of quantum theory, the one developed over the first half of the 20th century and refined since, time is not part of the system being described. Time is the external parameter that the system evolves through. The Schrödinger equation, the central equation of quantum mechanics, says that quantum states change as a function of time, but time itself is fixed. It flows uniformly and externally, a given rather than a variable. It is the coordinate system, not something the theory explains. When you try to quantize gravity, when you try to write a quantum theory of space-time itself, these two frameworks come into direct conflict. Quantum mechanics wants a fixed external time to evolve through. General relativity says there is no such thing as a fixed external time. The geometry of time is itself dynamic and physical. You cannot have both at once. And when you do the mathematics carefully, trying to write a constraint equation that respects both frameworks, something happens. Time cancels. The equation you get does not contain a time variable. The universe, treated as a quantum system, is described by a state that does not evolve. What makes this especially troubling, and what connects it back to the central question running through everything we are discussing here, is that this is not a failure of the mathematics. The mathematics is not broken. The equation is not wrong in the sense of producing contradictions or nonsense. It is internally consistent. It just describes a universe with no time in it. The discomfort that physicists feel when confronting the Wheeler-DeWitt equation is the discomfort of a result that works mathematically but refuses to fit our intuition about what reality is. And in physics, when the math works and the intuition fails, history is very clear about which one to trust. So if nobody chose to remove time, if time simply is not there when you do the calculation, the real question becomes not whether this is right, but what it means. And that question is considerably harder. Part 3, the silence inside the universe. Take the Wheeler-DeWitt equation at absolute face value for a moment. Not as an approximation, not as a useful tool, but as a literal description of what exists. What you get is a universe that does not happen. Events do not occur. Nothing causes anything else. The structure of reality, in this interpretation, is not a sequence of moments unfolding one after another. It is a single, frozen mathematical object. The universe does not evolve from a Big Bang toward a heat death. The Big Bang and the heat death, and every moment between them already exists simultaneously, fixed in place, the way all the frames of a film reel already exist on the spool before you press play. Physicists sometimes describe this with a phrase that sounds almost poetic until you realize it is meant technically. They say the universe simply is rather than becomes. There is no becoming. There is only being. And that distinction, which sounds like a philosophical quibble, turns out to carry enormous consequences for what we think reality is made of. Causality itself becomes suspect in this picture. The idea that A causes B, that earlier events produce later ones, depends on there being a meaningful direction called earlier and later. In a universe described by the Wheeler-DeWitt equation, that direction is not in the fundamental description. It might emerge at some level, the way temperature emerges from the motion of particles, but at the base level, the universe is not a chain of causes and effects. It is a structure, and we are somewhere inside it, experiencing the illusion of sequence. That idea that the disappearance of time from the deepest equation of physics is not a mathematical accident, but a window into the actual structure of reality, is what makes this more than a technical curiosity. It is sitting there, in the foundations, waiting. Part 4. The problem physicists avoid naming. There is a technical name for what we have been discussing, and it appears in the research literature often enough that it has its own shorthand. Physicists call it the problem of time, and it occupies a peculiar position in the world of theoretical physics, widely acknowledged, frequently cited, and almost never discussed openly in public-facing science communication. It is not a fringe concern. It is a central conceptual obstacle in every serious attempt to build a theory of quantum gravity, which is the missing unified framework that would reconcile general relativity and quantum mechanics into a single consistent description of nature. The problem is not simply that time disappears from the Wheeler-DeWitt equation. The deeper problem is that different approaches to quantum gravity handle time differently, and none of them agree on what time actually is at the fundamental level. Loop quantum gravity, which is one of the leading candidates for a quantum theory of space-time, reformulates the structure of space and time in terms of discrete geometric units and arrives at a similarly timeless fundamental description. String theory approaches the problem differently and runs into its own temporal difficulties. Causal set theory, which models space-time as a discrete partially ordered set, tries to build causality in from the beginning but still struggles with recovering a meaningful flow of time at large scales. What connects all of these approaches is the shared failure to find time as a primitive, unquestionable ingredient of the universe. In every serious attempt to write the deepest theory of physics, time either disappears, becomes ambiguous, or has to be reconstructed from something else. That pattern is not a coincidence, it is a signal. The reason physicists are reluctant to make strong public statements about this is not because they are hiding something. It is because there is no consensus on what comes next, on what replaces time, or how to recover it, or whether recovery is even the right goal. The problem of time is genuinely open, genuinely difficult, and pointing directly at the same conclusion from half a dozen different mathematical directions. Time may not be part of fundamental reality, and what to do with that possibility is a question physics has not yet answered. Part 5. The first crack in reality. If time is not in the equation, if it does not appear as a fundamental ingredient in the deepest mathematical description of the universe, then the obvious next move is to ask where it comes from. Not to abandon the experience of time, because clearly something is happening when you move from one moment to the next, but to ask whether that experience, that sensation of duration and sequence, is something that emerges from a timeless foundation rather than being a basic feature of reality itself. This is the shift that begins to crack everything open. Think about temperature. You know what temperature is. You have felt hot and cold your entire life. It is one of the most immediate physical sensations a human being can have. But if you look for temperature in the fundamental equations of physics, if you go down to the level of individual particles and ask where temperature lives, you do not find it. Temperature is not a property of a single particle. It is a statistical property of enormous numbers of particles. It is what happens when you have billions of atoms moving around, and you describe their average kinetic energy. Temperature is real in the sense that it has measurable effects and causes measurable outcomes, but it is not fundamental in the sense of being built into the basic rules. It emerges from something more elementary. What if time is the same kind of thing? What if the flow of time, the sense of before and after, the experience of duration and sequence, is not a basic feature of reality, but a large-scale pattern that emerges from something deeper and more fundamental that has no time in it at all? This is not a metaphor or an analogy being stretched for rhetorical effect. This is an active research direction in theoretical physics, being pursued seriously by serious people. The idea that time is emergent, that it arises from more primitive timeless structures rather than being built into the fabric of existence, is one of the most aggressively studied ideas in quantum gravity today, and it has some striking things going for it. The Wheeler-DeWitt equation, as we have established, contains no time. But when physicists look at approximate solutions to that equation, solutions that apply in regimes where the universe is large and classical, rather than tiny and quantum, something remarkable happens. Time-like behaviour reappears, not as a fundamental ingredient but as an emergent pattern. The large-scale, low-energy behaviour of the timeless equation looks like it has time in it, the same way the large-scale, high-temperature behaviour of a gas of particles looks like it has temperature in it. The time you experience every day may be the physics equivalent of a thermometer reading, accurate, useful, real in its effects, but not fundamental. This changes everything about how to think about the problem. If time is emergent, then the question is no longer why time disappears from the fundamental equations. That is expected. The question becomes, what is the timeless substrate from which time emerges, and what are the conditions under which that emergence breaks down? Because if time is an emergent property, then like all emergent properties, it should have regimes where it fails. There should be places or conditions where the approximation breaks down and the timeless reality beneath it becomes visible. There should be cracks, and there are. Black holes are one, the very early universe is another. The extreme conditions at the boundary of quantum gravity, wherever that boundary lies, are a third. These are the places where the emergent time description should start to fail, where the classical approximation that generates the experience of sequence and duration breaks down, and where you might begin to see the timeless structure underneath. Whether we can observe those cracks, whether we have the experimental tools to probe those regimes, is one of the most urgent questions in physics right now. What replaces time at the fundamental level in the frameworks where it is treated as emergent? That depends on who you ask. Some physicists point to entropy in thermodynamics, some point to quantum entanglement, some point to relational structures between physical processes. The fact that there are multiple competing answers is not a sign that the question is wrong. It is a sign that it is exactly right, that we are standing at the edge of something real, looking into a terrain where our current maps are inadequate, and that just ahead of us, in the mathematics and the experiments now being designed, there may be an answer to the most dangerous question physics has ever seriously entertained. What is reality made of, if not time? Part 6. Time as an emergent property. Temperature does not exist at the level of a single atom. Pull one hydrogen atom out of the air in the room where you're sitting and ask what temperature it is, and the question has no answer. Temperature is not a property that individual particles possess. It is a property that enormous collections of particles produce collectively, statistically, through their combined behaviour. It is real, genuinely, measurably, consequentially real, but it is real in the way that rush hour is real. Rush hour is not a property of any single car. It is a pattern that emerges from many cars interacting in a particular context, and it has real effects on how long it takes you to get home. But it is not fundamental. There is no rush hour particle. There is no temperature field written into the basic laws of physics. These things emerge from something more elementary. Now hold that thought and walk it directly into the problem of time. At the scale of individual particles, at the quantum scale where the Wheeler-DeWitt equation lives, no flowing time is detectable in the equations. The fundamental laws of physics are, with one partial exception we will get to shortly, time symmetric. They work the same in both directions. If you filmed a collision between two fundamental particles and then played the film backward, the reversed collision would look just as physically valid as the forward one. The laws do not prefer a direction. There is no built-in arrow pointing from past to future. There is no fundamental equation that says this moment comes before that one. At the most basic level, physics is timeless in a very specific sense. It has no preferred direction of time and no mechanism that requires one moment to follow from another. And yet you know, with absolute certainty, that the video of someone breaking a glass plays forward and not backward. You know that the past is fixed and the future is open. You know that you age in one direction and not the other. That directionality, the arrow of time, the asymmetry between past and future that defines every experience you have ever had is not written into the fundamental equations. It emerges. And the thing it emerges from is entropy. Entropy is a measure of disorder, of how many ways a physical system can be arranged while still looking the same at large scales. A cup of coffee with milk uniformly distributed throughout it has higher entropy than one where the milk is in a separate spiral. There are more ways to arrange the molecules so that the milk looks uniformly mixed than there are ways to arrange them so the milk is in a spiral. The second law of thermodynamics says entropy tends to increase, not because the laws of physics demand it in any fundamental sense, but because there are simply more ways for a system to be disordered than ordered, and so random processes tend to push systems toward disorder over time. The direction of increasing entropy, from lower disorder to higher disorder, is what gives time its arrow. The future is the direction in which entropy increases. The past is the direction from which it came. What this means is staggering when you sit with it. The thing you feel most intimately, the flow of time, the sense that this moment is happening and the next one is coming, is not written into the basic fabric of physics. It is a statistical phenomenon. It arises because the universe happened to start in a state of extremely low entropy, and has been moving toward higher entropy ever since, and that gradient of disorder is what your brain reads as the passage of time. You're a thermometer, in a sense. You're a measuring device that detects the direction of increasing entropy and encodes it as the experience of moving forward through time. This solves some paradoxes beautifully. It explains why the microscopic laws are time-symmetric, but the macroscopic experience of time is not. It explains why you remember the past and not the future. The past is the low-entropy direction, and your memory is a low-entropy record of what came from it. But it does not solve everything. It does not explain why the universe started in such an extraordinarily low-entropy state to begin with. That initial condition, sometimes called the past hypothesis, is not itself explained by entropy arguments. It is just assumed. And it does not explain why emergence feels so real, why a statistical pattern produces something as vivid and immediate as the sensation of now. If time is an emergent statistical phenomenon, then it should have limits. There should be regimes where the statistical approximation breaks down, where the emergent time description fails, and the timeless foundation becomes relevant. And if that is right, if the flow of time you feel right now is a large-scale approximation of something fundamentally different, then there are places in the universe where that approximation is currently failing. Places where time, as a useful description, stops working. That is not a metaphor. That is a prediction. And it connects back to the central thread of everything being laid out here. Because if time is emergent rather than fundamental, then the Wheeler-DeWitt equation's silence about time is not a puzzle to be explained away. It is a description of what is actually there. Part 7. The Relational Universe. Carlo Rovelli is one of the physicists who has pushed farthest into the territory of what a timeless universe actually looks like, and his answer is both simpler and more radical than you might expect. Rovelli's position, developed through his work on loop quantum gravity and elaborated in a series of books and papers over several decades, is that time is not an independently existing thing at all. It is a description of relationships between physical processes. Time is not the container that events happen inside. Time is what you get when you compare one process to another. Think about what a clock actually does. A clock does not measure the flow of some abstract external time. It performs a physical process, the oscillation of a quartz crystal, the vibration of cesium atoms, the swing of a pendulum, and you use that process as a reference to compare against other processes. When you say it is 3 in the afternoon, you're saying that a certain number of oscillations have occurred inside your clock since some agreed upon reference point. You're describing a relationship between physical processes, not accessing some cosmic timestamp. Rovelli's argument is that this is all time ever is. There is no universal now. There is no absolute timeline that the universe is progressing through. There are only physical processes and the relationships between them, and what we call time is the name we give to those relationships when we measure them. The philosophical consequences are immediate and vertiginous. If time is purely relational, there is no single consistent answer to what time it is everywhere in the universe right now. Not because of the relativity effects Einstein described, though those are real too, but because now is not a feature of the universe. It is a feature of an observer embedded in a specific set of physical relationships. Your now is the intersection of the processes you are currently in contact with. My now is mine. Neither is the universe's now, because the universe does not have one. And this connects back to what the Wheeler-DeWitt equation is telling us. A universe described without time is a universe that does not have a global clock ticking somewhere. A universe whose deepest description is precisely what a relational view predicts. Part 8. The block universe trap. Einstein almost certainly believed in what physicists call the block universe. There is a well-known exchange from near the end of Einstein's life, following the death of his lifelong friend Michel Besso, in which Einstein wrote to Besso's family that Besso had preceded him only slightly in leaving this strange world, and that the distinction between past, present and future is only a stubbornly persistent illusion. Whether Einstein meant this as physics or consolation has been debated, but the physics he developed makes the statement look less like poetry and more like a rigorous conclusion. Here is what general relativity implies about the structure of time. In special relativity, the simpler precursor to general relativity, developed in 1905, Einstein showed that the concept of simultaneity is not absolute. Two events that happen at the same time in one reference frame do not happen at the same time in another reference frame moving relative to the first. This is not a measurement error. It is not an illusion created by signal delay. It is a fundamental feature of how space-time geometry works. Different observers genuinely disagree about the order of events, and all of their orderings are equally valid. This has a consequence that is usually underemphasized in popular accounts. If there is no absolute definition of which events are happening now, if now is observer-dependent rather than universal, then the division of space-time into past, present and future is not a feature of space-time itself. It is a feature of the perspective of a particular observer. And if that is the case, then all moments in time exist on the same footing. Your childhood, this present moment, the moment of your death, and every moment between them are all equally real parts of a four-dimensional structure called space-time. None of them is more present than another in any absolute sense. The one that feels present is the one your consciousness is currently processing. But the others are there. They are as real as any spatial location you are not currently occupying. This is the block universe. Physicists call it that because the picture it suggests is of all of space-time as a single, fixed, four-dimensional block, with time as one of its dimensions in the same way that left, right or up, down are dimensions. You're not moving through time. You're a four-dimensional structure extended through time the same way you're extended through space. The experience of motion through time, the feeling of being at this moment now, and then a moment later being at the next moment now, is not the universe advancing. It is your consciousness processing successive slices of a structure that already exists in its entirety. The film reel analogy helps here. Imagine a film reel lying on a table. Every frame of the movie already exists, from the first to the last, simultaneously present on the physical reel. When you thread it through a projector and watch it, you experience the frames as a sequence, as motion, as story. But the reel did not change while you watched. All the frames were always there. The projector just revealed them one at a time. The block universe says the same thing about space-time. All the moments already exist. Your consciousness is the projector, moving through the reel, experiencing sequence and duration. But the reel, the four-dimensional space-time structure, is static. Now here is the uncomfortable part. Most physicists who take general relativity seriously and think carefully about its implications accept some version of the block universe view, or at least find it very difficult to avoid. It follows so directly from the relativity of simultaneity that rejecting it requires adding extra structure to the theory that the theory itself does not provide. And yet the block universe means something specific about the experience of time. It means that what you feel as the flow of time, that sense of being swept forward into the future, is not a feature of the universe. It is a feature of consciousness. The universe is not flowing. You are not moving. The present moment is not special in any absolute sense. It is just the frame of the film reel that happens to be in the projector window right now. And this circles back to the Wheeler-DeWitt equation with a new kind of clarity. A timeless universe, a universe described by an equation with no time variable, is exactly what a block universe should look like at the fundamental level. the equation is not missing time. It is describing a static structure correctly. The time we experience is the projector window, not the real. And the question of whether the projector is real, of whether the flow is genuine or constructed, is something we're only just beginning to have the experimental tools to probe. Part 9. Why you still feel time. If time is emergent, if it is relational, if the block universe description is correct and all moments exist simultaneously in a static four-dimensional structure, then why do you feel time so vividly? Why is the experience of duration, of one moment following another, so immediate and so convincing? Why does it feel like the most real thing there is, rather than an illusion generated by a brain processing a timeless structure? Neuroscience has a partial answer, and it is instructive about the mechanisms involved, even if it does not fully resolve the deeper metaphysical question. Your brain does not have direct access to time, it has access to memories. The past in your subjective experience is not directly perceived, it is reconstructed from records stored in neural connections. When you remember what you had for breakfast, you are not accessing a direct pipeline to this morning. You're activating a pattern of neural activity that was laid down this morning and that represents a compressed, interpreted record of what happened. Memory is not a recording, it is a reconstruction. And the future, similarly, is not something you perceive. It is something your brain constructs through prediction, through extrapolating from past patterns to anticipate what will happen next. What your brain calls the present is a window of integration, a span of approximately 2 to 3 seconds during which sensory input, memory and prediction are combined into a unified experience of now. You're not experiencing this exact instant. You're experiencing a slightly delayed, heavily processed, narratively smoothed representation of a brief interval around this instant, constructed by a brain whose primary job is to make sense of change in the service of survival. This matters for the physics because it suggests that the experience of time flow is a cognitive product rather than a direct perception of physical reality. You do not feel time the way you feel heat on your skin. You construct the experience of time the way you construct the plot of a novel from marks on a page. The marks are real, the plot is real in its effects, but the plot is not in the marks in the way that heat is in the fire, it is in the reader, and if subjective time is in the brain the way a plot is in the reader, then the absence of time from the fundamental equations of physics is not a contradiction of experience, it is a description of what experience is built on top of. Part 10. The dangerous shift. Everything discussed so far, the Wheeler-DeWitt equation, emergent time, the block universe, the neuroscience of temporal experience, lives primarily in the domain of theory. Consistent theory, well-motivated theory, theory with serious mathematical support, but theory nonetheless. The step that turns this from a fascinating intellectual puzzle into something genuinely urgent and testable is the recognition that if time is emergent, it is not just a philosophical claim, it is a physical prediction, and physical predictions can break. Emergent properties have a characteristic behaviour under extreme conditions. They hold in the regimes where they are valid approximations, and they fail in the regimes where the underlying structure dominates. Temperature holds perfectly well at everyday scales and breaks down when you get to a single particle. Hydrodynamics, the physics of fluids, holds well at the scales of rivers and oceans and breaks down at the molecular scale where the fluid approximation fails. If time is an emergent property of a timeless fundamental structure, then it too should have a breakdown regime. There should be conditions under which the time description fails and the timeless foundation becomes the relevant description. Those conditions are not hypothetical. They correspond to real physical situations that exist in the universe. At the singularity inside a black hole, the curvature of space-time becomes infinite, and every known physical description breaks down, including the time description. At the Planck scale, the incredibly small scale, about 10 to the minus 35 meters, where quantum gravitational effects become dominant, the smooth space-time geometry of general relativity is expected to dissolve into something else entirely, and that something else may have no time in it. In the very first instance after the Big Bang, when the entire observable universe was compressed into a region smaller than a proton and quantum gravitational effects dominated, the time description may not have been valid at all. The universe may not have had a beginning in time so much as a beginning of time, a region where the emergent time description first became applicable as the universe expanded and cooled to a scale where the approximation held. These are not distant abstractions. They are predictions, and increasingly they are becoming testable. Experiments in quantum timekeeping, attempts to probe the finest grains of temporal measurement, are beginning to reach the scales where quantum effects on time itself become observable. The theoretical frontier and the experimental frontier are converging. What was once a purely mathematical curiosity is becoming something you might be able to measure. And when you measure it, when you actually probe the finest edges of what time is, what you find raises questions that nobody in physics was fully prepared for. Part 11. The smallest clock ever built. In 2025, something happened in a laboratory at the University of Oxford that did not make the front pages of newspapers, but should have kept a lot of physicists awake at night. Researchers working on quantum timekeeping, on the limits of how precisely and at what scale time can be measured, were exploring what happens when you push a clock down to the smallest possible physical scale. Not a clock in the everyday sense, not even in the sense of an atomic clock, which is already extraordinarily precise, but a clock in the deepest theoretical sense, a physical system whose evolution you track as a measure of duration. The question they were pursuing is one that sounds almost philosophical until you realise it is entirely concrete. Every clock is a physical process. Every clock requires some physical system, an oscillating crystal, a vibrating atom, a spinning particle, whose regular behaviour you use as a reference. The precision of the clock depends on how regular and how fast that behaviour is. Modern atomic clocks, which use the oscillation of cesium atoms, are accurate to about 1 second in 300 million years. They are the most precise measuring instruments human beings have ever constructed, but they are still far from the theoretical limit of timekeeping precision, which is set not by engineering challenges but by quantum mechanics itself. What happens when you try to build a clock that operates at the quantum scale, at the level of a single particle, a single electron, where quantum effects are not a small correction, but the dominant physics? What happens when you try to read time from the smallest possible physical oscillator? These are not purely theoretical questions. They are experimentally accessible, and the results that have been emerging from quantum metrology research in recent years point towards something deeply strange. What the Oxford Research Programme and related theoretical work suggests is this. At the quantum scale, the relationship between the size of a clock and the energy required to operate it is not what you would naively expect. For a classical clock, there is a reasonable proportionality. A smaller clock requires less energy. But at quantum scales, something changes. The energy required to read the clock, to actually extract information about what time it is from the quantum system, scales in a way that becomes disproportionately large as the clock becomes small. The measurement itself, the act of reading the time, costs more energy than the physical process being used to keep time. This is not an engineering problem. It is not the result of inefficiency in the measurement apparatus. It is a fundamental feature of quantum mechanics. At the quantum scale, measuring a system requires interacting with it, and interacting with it disturbs it. For macroscopic clocks, this disturbance is negligible. The clock is so large and robust that the measurement barely affects it. But for a quantum scale clock, the measurement is comparable in energy to the process being measured. And according to the results from this research program, for a clock at the smallest physically meaningful scales, a clock running on a single particle, the energy required just to extract a reading from the clock can be on the order of 1 billion times greater than the energy the clock itself uses to run. 1 billion times. Let that scale sink in for a moment. A clock that runs on an amount of energy so small you could not detect it with any existing instrument requires an amount of energy to read that would be detectable very clearly. The act of asking what time it is costs orders of magnitude more than the cost of time passing, and this is not a curiosity or an anomaly, it is a clue. A clue about the relationship between time, information and energy at the most fundamental scales, and about why the Wheeler-DeWitt equation, the equation that describes the whole universe, might not need a time variable. If reading time costs more than time itself, perhaps at the level of the universe as a whole, there is no external reader. There is no observer outside the universe to pay the energy cost of measurement. And so time, for the universe as a quantum system, may simply not be a defined quantity. Part 12. The measurement paradox. The finding from quantum clock research that the energy cost of reading a clock at quantum scales vastly exceeds the energy cost of running it is a specific instance of something more general and more unsettling that has been sitting inside quantum mechanics since its earliest days. The observer is not passive, measurement is not neutral, looking at something changes it. This was already known. What the quantum clock results add is a quantitative sharpness to what that means when the thing you're looking at is time itself. In standard quantum mechanics, every measurement you make on a quantum system involves an interaction between the system and the measurement apparatus. That interaction is physical. It involves energy exchange. It causes what physicists call wave function collapse. The system, which was in a superposition of possible states before the measurement, is forced into a definite state by the interaction. You do not passively read a value off a quantum system. You physically collide with it, and the collision produces a definite outcome, while simultaneously disturbing the system's prior state. For most quantum experiments, this is manageable. You design your measurements carefully, account for the disturbance, and work with the resulting data. But for a quantum clock, a system you're trying to use to measure time, the measurement paradox bites hard. Every time you read the clock, you disturb the process that constitutes the clock. You change the quantum state that the clock's timekeeping depends on. The act of asking what time it is alters what time it is, in a precise and physically meaningful sense. And because the energy cost of the measurement is so much larger than the energy cost of the clock's operation, the disturbance is not a small correction. It is a dominant effect. This has a direct connection to the central question about whether time is real at the fundamental level. If reading time requires physical interaction, and if physical interaction is required for time to have a definite value, then time, at least at the quantum scale, is not a property that exists independently of measurement. It is a property that is produced by measurement. Before you interact with the clock, the time is not well defined. It exists as a quantum superposition of possible values. The measurement collapses it into a specific answer. Time, at the quantum level, may be something that happens when you look, not something that is there whether you look or not. Part 13. Observation versus reality. The measurement paradox in quantum clocks is a specific version of the deepest and most contested problem in all of physics, the quantum measurement problem. This is the question of what actually happens when a quantum system, which can exist in a superposition of states, is measured and produces a definite outcome. The mathematics of quantum mechanics, the Schrödinger equation, describes how quantum states evolve. But it predicts that a quantum system in superposition should remain in superposition indefinitely, evolving smoothly and continuously according to the wave equation. A definite measurement result, a specific number, a single answer, should not emerge from that evolution. And yet it does. Every time you measure something, you get a specific answer. The superposition collapses to a definite state. The question is, what causes that collapse? And the answer that physics has provided over the decades is, embarrassingly, still contested. The oldest interpretation, the Copenhagen interpretation developed by Niels Bohr and Werner Heisenberg in the 1920s, says that the collapse happens when a measurement is made, and defines measurement as involving a classical observer interacting with the quantum system. But it notoriously refuses to specify what counts as an observer or what the physical mechanism of collapse is. It works perfectly well as a calculational recipe. It tells you how to compute the probabilities of measurement outcomes, and it always gives you the right answers. But it says nothing about what is actually happening in the world when a measurement occurs. More recent interpretations have tried to do better. The many worlds interpretation, developed by Hugh Everett in 1957, says that collapse never happens. Instead, the universe branches every time a measurement is made, with all possible outcomes occurring in separate branches. The relational interpretation, developed partly by Ravelli, says that quantum states are always defined relative to an observer, and collapse represents an update in the observer's information about the system. The decoherence program tries to explain the appearance of collapse through the interaction of quantum systems with their environments, without invoking any special observer or collapse mechanism. What connects all of these interpretations to the question of time is that they all, in different ways, suggest that time at the quantum level is not independent of the interactions and observations that constitute experience. In the Copenhagen view, definite events only happen when observers make measurements, which means definiteness, the existence of specific facts about the world, depends on observation. In the relational view, all facts are relative to observers, and time is a relational fact like any other. In the many worlds view, all outcomes are equally real, and the experienced passage of time is the particular sequence of branches that your thread of consciousness happens to traverse. In every case, the notion of an objective time ticking along independently of any observer or interaction becomes at least questionable and in some interpretations incoherent. There is an informational way to frame all of this that some physicists find more tractable. Reality in this framing is fundamentally about information. Not information in the colloquial sense of data or knowledge, but information in the technical sense. The correlations between physical systems that are established when those systems interact. Time, in this picture, is not a river flowing from the past to the future. It is a record, a set of correlations between current physical states and past physical configurations. The past exists in the present not as a direct metaphysical reality, but as information encoded in the current state of the universe. And the future exists in the present as the space of possible future correlations that the current state can generate. This framing has a radical implication that connects back to everything being discussed here. If time is informational, if past and future are descriptions of correlation structures rather than existing regions of reality, then the Wheeler-DeWitt equation's silence about time makes perfect sense. A timeless equation describing a static quantum state is exactly what you would expect if the universe is, at its foundation, an information structure rather than a temporal sequence. Time emerges from the information the way temperature emerges from particle velocities. The universe does not have a time variable because it does not move through time. It is time in the sense that time is a description of the informational relationships inside it. Part 14. The hidden cost of a second. Every clock you have ever used, every sundial, hourglass, pendulum, quartz oscillator, cesium fountain, GPS receiver relies on the same basic physical fact. Physical processes have characteristic rates. Atoms vibrate at specific frequencies. Light completes oscillations at regular intervals. Particles decay at statistically predictable rates. All of these are physical processes and all of them require energy to sustain. The cesium atom that defines the International Atomic Time Standard oscillates about 9,192,631,770 times per second. Those oscillations are not free. They are maintained by the quantum mechanical ground state of the cesium atom, which has a specific energy, and accessing that energy for measurement requires precisely calibrated interactions with electromagnetic fields. There is no such thing as a free timekeeping process. Every measurement of time, every determination of how much duration has passed between two events, requires an exchange of energy with a physical system. At everyday scales, this energy cost is negligibly small. But at quantum scales, as the Oxford Research Programme has shown, the cost becomes dominant. The price of a second, the physical energy investment required to establish that 1 second has elapsed becomes enormous when the clock is small enough. What this suggests about the fundamental nature of time is something that nobody fully anticipated. Time is not passive. Time is not an inert backdrop that physical processes play out against. Time, at the quantum scale, is something that physical interactions produce, at a cost, through the process of measurement and information exchange. The second you just experienced did not come for free. It came at the cost of countless physical interactions, in your body, in the measuring instruments around you, in the light bouncing off objects in your field of vision, each of which extracted a tiny amount of information from the physical environment and encoded it as temporal experience. And at the most fundamental scale, where those interactions approach their quantum mechanical limits, the cost per unit of temporal information becomes not small but enormous. Part 15, the collapse of objective time. Bringing together everything from this section, the quantum clock energy paradox, the measurement problem, the informational view of reality, the fundamental cost of timekeeping. What emerges is a picture in which objective, universal, observer-independent time becomes increasingly difficult to defend. And that difficulty is not the kind that comes from incomplete data or insufficient technology. It is the kind that comes from the mathematics and the experiments pointing, repeatedly and from different directions, toward the same uncomfortable conclusion. Time, as a fixed and universal feature of reality, may be a story we tell ourselves. A very good story, an extremely useful story, a story so consistent and so reliable at the scales we inhabit that questioning it feels almost absurd, but a story nonetheless. At everyday scales, the approximation holds perfectly. Time flows, clocks agree, events have well-defined order, and the universe seems to have a coherent present moment moving forward into the future. You wake up, the clock reads 7 in the morning, you remember yesterday, you anticipate tomorrow, and the whole framework hangs together with a consistency so complete that doubting it requires a deliberate act of intellectual effort. But that agreement, that seamless, reliable, universal-seeming tick of the clock, is an emergent property of classical scale systems, all subject to the same thermodynamic arrow, all reading the same large-scale entropy gradient, all embedded in the same region of space-time geometry. It is real in the same way that rush hour is real, a genuine pattern with genuine effects, something you would be foolish to ignore when planning your commute, but it is not fundamental. Rush hour does not appear in the equations of motion for individual cars. Time does not appear in the Wheeler-DeWitt equation for the universe. The pattern is real. The foundation it sits on is something else entirely. At the quantum scale, objective time dissolves in ways that are precise and measurable, rather than merely philosophical. A quantum system does not have a definite time until it is measured. Before measurement, the time associated with a quantum clock exists as a superposition of possibilities, a spread of potential values with associated probabilities, none of them definite, none of them real in the classical sense until an interaction collapses the superposition into a specific outcome. Measuring it costs energy that the system itself does not contain. As the Oxford quantum clock research demonstrated, the energy required to read the time from a quantum scale clock can exceed the energy used to run the clock by factors that, at the smallest scales, approach 1 billion to 1. The act of measurement disturbs the very process being used to measure time, introducing uncertainties that are not engineering limitations, but fundamental features of quantum mechanics. You cannot passively read time at the quantum scale. You have to reach in and grab it, and the grabbing changes what you find. Two quantum systems isolated from each other can evolve in ways that are entirely incompatible with any shared time description. If you take two quantum clocks, isolate them completely from each other and from any common reference, and then ask whether they agree on how much time has passed, quantum mechanics does not guarantee a consistent answer. There is no quantum equivalent of synchronizing your watch before you leave for the expedition. There is no quantum Greenwich Mean Time, The global, universal, everyone agrees on the same now picture of time that Newton assumed, and that we still implicitly rely on in everyday life, has no quantum mechanical foundation. It is an approximation that holds when systems are large enough and classical enough to behave like the average of their quantum states. Beneath that approximation, temporal agreement between isolated systems is not guaranteed by physics. It is a lucky consequence of the scale we happen to inhabit. In extreme physical regimes, the situation becomes more severe. Inside black holes, at the Big Bang singularity, at the Planck scale where quantum gravitational effects dominate, at these extremes, even the classical emergent time description breaks down completely. The smooth space-time geometry that provides the framework for relativistic time disappears. General relativity, which treats time as a dimension of a smooth four-dimensional manifold, predicts its own failure at these points. The equations produce infinities, values that are not just large but literally undefined, and infinities in physics are always a signal that the theory has reached the boundary of its validity and something new is needed. What replaces the smooth space-time geometry at these extremes is unknown, because we do not yet have a complete theory of quantum gravity. That theory, the missing unified framework that would reconcile general relativity with quantum mechanics, is the central unsolved problem in theoretical physics. But every serious candidate for that theory, loop quantum gravity, string theory approaches, causal set theory, causal dynamical triangulations, shares one feature. Whatever they put in place of smooth space-time geometry at the Planck scale, it does not contain time as a fundamental ingredient. Time, in every serious candidate for the deepest theory of physics, is something that has to be recovered, reconstructed, or explained rather than assumed. That convergence is not accidental. When multiple completely different mathematical approaches to the same problem arrive at the same answer, that is one of the strongest signals physics has that the answer is pointing at something real. This something real in this case is the absence of time at the foundation of the universe. There is something worth pausing on here, because the natural response to everything just described is a kind of intellectual vertigo, a feeling that the ground has shifted and it is not clear where to stand. That response is appropriate. What is being described is not a minor revision to our picture of the universe. It is not a correction to the edges of physics while the centre holds. It is a challenge to the most basic structural assumption in all of science, that there is a time variable, that it flows, that events are ordered along it, and that this ordering is objective and universal. Every equation in physics, every experiment ever conducted, every prediction ever made assumes some version of this. And now the mathematics of the deepest attempted unification of physics is saying that the assumption may not be valid at the foundational level. The collapse of objective time is not a conclusion that physics has reached. It is a direction that physics is moving in, with increasing confidence and increasing experimental traction, driven by results that nobody fully anticipated and that the field is still working to absorb. The quantum clock experiments are not finished. The quantum gravity research programs are not finished. The theoretical frameworks for emergent time are not finished. What we have right now is a picture that is coming into focus rather than a picture that is complete, and what is becoming visible in that picture is stranger and more radical than the headline version of the story usually conveys. The question that the collapse of objective time leaves behind is not rhetorical. It is not a provocative closing line for a popular science article. It is the most urgent question in theoretical physics right now, being actively pursued by serious researchers at the best institutions in the world, driving experimental programs and theoretical frameworks and debates that will shape the next generation of fundamental physics. If time is not fundamental, not universal, and not observer-independent, then what is the universe made of? What is the timeless substrate from which time emerges? What are the elementary ingredients of a reality that generates the experience of duration without containing duration at its foundation? The answers being explored are stranger than most people have been told, and they are waiting just ahead in the final act of this story In a picture of the universe that has no becoming, only being, no causality that is not reconstructed from something deeper, and a radical possibility about the relationship between time, information, and the existence of observers that may be the most quietly destabilizing idea physics has ever seriously entertained. Part 16. A universe without becoming. Try to imagine a universe without becoming. Not a universe where time is slow, or where time is strange, or where time has unusual properties, but a universe where the concept of something happening, of one state of affairs giving way to another, simply does not apply at the fundamental level. Not as a philosophical exercise, but as a literal description of what the Wheeler-DeWitt equation and the block universe and the emergent time program are collectively pointing toward. This is not a thought experiment designed to produce discomfort and then be walked back. This is where the mathematics leads when you follow it honestly, without flinching. To the end of the road it is pointing down. It helps to start with something concrete. Think about the most ordinary sequence of events you can imagine. You pick up a glass of water. You bring it to your lips. You drink. 3 moments, 3 states of the world, each one following from the previous one in a chain of cause and effect so simple and so immediate that calling it a sequence of events feels almost comically obvious. Of course, those 3 moments happened in order. Of course, the drinking followed the lifting. Of course, there was a before and an after. The entire structure of your experience, of language, of memory, of planning, of science itself, is built on the assumption that this kind of sequencing is real and fundamental, that the universe moves from one state to the next, the way a sentence moves from one word to the next. Now take that assumption and ask whether it appears anywhere in the Wheeler-DeWitt equation. It does not. Take it and ask whether the block universe, which follows directly from general relativity, supports it. It does not in the block universe. All 3 moments of your drink of water already exist simultaneously as fixed features of a 4-dimensional structure, and the sequence is a property of how your consciousness processes those features, not a property of the features themselves. Take it and ask whether the emergent time program treats sequencing as fundamental. It does not in that program. The appearance of sequential change emerges statistically from a timeless foundation, the way the apparent flow of a river emerges from the statistical behavior of water molecules that individually have no concept of downstream. In that universe, and according to the physics we have been examining, this may be the universe. There are no events. There are only configurations. A configuration is a complete specification of the state of everything, a total snapshot of the entire physical structure of reality at a given level of description. In a universe with time, configurations follow one another. Each configuration causes the next through the operation of physical laws, and the sequence of configurations constitutes what we call history, what we call the past, what we call the story of how things came to be the way they are. The laws of physics in this picture are rules for moving from one configuration to the next. They are the grammar of becoming. In a universe without time, there is no sequence. There is no grammar of becoming because there is no becoming to grammatize. There is only a single, static, total configuration, or more precisely, in the quantum mechanical picture that the Wheeler-DeWitt equation provides, a quantum state that encodes all possible configurations simultaneously with specific probability amplitudes, none of which is more present than any other, none of which is happening now in any absolute sense. The quantum state of the universe in this picture is not a description of what is happening. It is a description of what is. All of it, at once. The Big Bang and the formation of the first stars and the emergence of life in this exact moment and everything that comes after, all of it encoded in a single timeless quantum state, related to each other not by sequence but by the mathematical structure of the wave function. You're not living through a sequence of moments. In this picture, you are a feature of a configuration. You are a specific, extraordinarily complex pattern of matter and energy and information that exists as part of the total quantum state of the universe, and the properties you have, including your memories, your anticipations, your sense of being in the middle of something are properties of that pattern, not properties of a process unfolding through time. Your memories of yesterday exist not because yesterday happened and you recorded it in a sequential diary of experience, but because you are a configuration that contains, encoded in the physical structure of your neural connections, a record of a lower entropy configuration that is part of the same static quantum state. The record is real. The encoding is real. The physical differences between your brain before and after a memory is formed are real. But the process of forming the memory, the sense of yesterday actually occurring and being captured, is a feature of the configuration you are, not evidence of the universe moving forward through time. Your anticipation of tomorrow works the same way, and this is perhaps the stranger of the two directions. Tomorrow feels open. It feels genuinely undetermined. It feels like a space of possibilities that has not yet collapsed into actuality, a field of potential futures, any one of which might be the one you end up living. That feeling of openness, of genuine contingency, of the future being real but not yet fixed, that phenomenology is one of the most powerful arguments that the block universe and the timeless universe cannot be right. If everything is already fixed in a static structure, how can the future feel open? How can choice feel real? How can the next moment feel like something that is about to happen rather than something that already exists waiting? Your anticipation of tomorrow exists not because tomorrow will happen in a sequential sense, but because you are a configuration that contains a prediction structure, a neural and cognitive architecture shaped by evolution and experience to model possible future configurations and assign probabilities to them. The openness you feel is the openness of the model, not the openness of reality. Your brain evolved in a world where predicting the future was the difference between surviving and not surviving, and so it generates an extraordinarily vivid and compelling experience of the future as open and the past is fixed. That asymmetry, fixed past, open future, is the experiential signature of the entropy gradient, of the thermodynamic arrow that gives emergent time its direction. It is not a window onto the fundamental structure of reality. It is a feature of the particular configuration you are, embedded in a particular region of the total quantum state, processing the information available to that region in the way that biological information processing systems do. The experience of duration, of time passing between yesterday and tomorrow, of this moment being sandwiched between what came before and what comes after, is a property of the configuration you are, not a property of reality moving through time. Duration is in you the way temperature is in the thermometer, not the way mass is in the object being weighed. It is a readout, not an ingredient. This is the universe without becoming, a universe that simply is. Everything that ever happened and everything that will ever happen, coexisting in a single timeless structure, with no privileged present moment, no process of change, no direction of before and after, that is built into the foundation rather than emerging from the statistics of large systems. Change is not something the universe does. Change is something the universe contains a description of, written into the relations between different parts of the same static structure, the way the plot of a novel is written into the relations between different pages, real as a description, absent as a process. The emotional dissonance this produces is worth sitting with rather than dismissing, because the dissonance is itself data. You feel right now that things are happening, that you're in the middle of something, that the next moment is genuinely open, genuinely undetermined, and that you're about to live it in a way that is not yet settled. That feeling, that phenomenology of openness and forward motion and presence, is not addressed by the physics in any direct way. The physics says the structure is static. The experience says it is dynamic. The physics says all moments are equally real. The experience says this one is special. The physics says becoming is not fundamental. The experience says becoming is the most fundamental thing there is. Whether the physics is wrong in some way we have not yet identified, or the experience is a construction generated by a static structure, in a way that makes the construction feel indistinguishable from reality, or whether we are missing a piece of the puzzle that would reconcile the two in a framework none of the current theories have yet reached. That is exactly the fault line that makes this the most dangerous idea in physics. Not dangerous because it is certainly false and people might believe it anyway. Dangerous because it might be true, the evidence keeps accumulating in its direction, and we do not yet know what to do with a universe in which the most intimate and undeniable feature of being alive turns out to be something the universe itself, at its deepest level, does not contain. Part 17. Causality under threat. One of the things that depends most directly on time having a real and objective existence is causality. The idea that A causes B, that earlier events produce later events, that the past is responsible for the present, requires a time ordering. Cause comes before effect. The timeline provides the arrow of explanation. Remove the timeline, or make it observer-dependent, or replace it with a static structure in which all moments coexist, and causality becomes something that needs to be reconstructed rather than something given. And that reconstruction, it turns out, is harder than it sounds, because causality is not just a feature of physics. It is the skeleton of every explanation we have ever given for anything. Think about what causality actually does for us. It is not just a philosophical convenience. It is the operating system of science, of medicine, of engineering, of history, of law, of every domain of human knowledge that involves explaining why something happened or predicting what will happen next. When a doctor tells you that smoking causes cancer, they are making a causal claim, that the presence of smoking in the past produces a higher probability of cancer in the future, through a chain of physical mechanisms that respect the direction of time. When an engineer designs a bridge, every calculation assumes that the forces applied now will produce the structural responses later in a reliable and predictable sequence. When a court of law assigns responsibility for an event, the entire framework of legal reasoning depends on the idea that earlier actions produce later consequences, and that the relationship between them is not just correlation, but genuine causation with direction. All of that, every bit of it, sits on top of the assumption that time is real, objective, and ordered. That before and after are not observer-dependent descriptions, but features of the universe itself. And that assumption, as we have been examining, is precisely what the deepest frameworks in physics are now putting under pressure. In the block universe picture, causality is already somewhat reframed, and the reframing is subtle enough that it is worth taking slowly. Rather than events producing each other sequentially, rather than the past literally reaching forward through time to bring the present into existence, the block universe contains a pattern of correlations between events at different locations in space-time. The entire four-dimensional structure exists at once, static and complete, and what we call causality is the pattern of these correlations, the fact that certain configurations of matter and energy at certain space-time locations are correlated with specific configurations at other space-time locations in ways that are constrained by the laws of physics. The billiard ball that was struck at 3 in the afternoon is correlated with the billiard ball that moved at 3 in the afternoon and a fraction of a second. That correlation is real. It is encoded in the geometry of the block universe. But the striking did not produce the moving in a sequential generative sense, not in the way we intuitively imagine, where the cause reaches through time and brings the effect into being. Both events already exist in the four-dimensional structure. The correlation between them is a geometric feature of that structure. We experience it as causation because we are observers embedded in the structure, moving through it in the time direction, encountering the correlations in sequence, and our brains, built by evolution to predict and explain, interpret the sequence of correlations as a chain of causes and effects. Causality in the block universe is something like a shadow. The shadow is real. It falls in predictable places. It responds to the shapes of objects in lawful and consistent ways. But the shadow is not a thing in itself. It is a projection, a pattern cast by the geometry of the structure onto the screen of temporal experience. Remove the observer moving through time, and the shadow does not disappear from the structure. It was never in the structure to begin with. It was always in the experience of traversing it. In more radical, timeless frameworks, the ones that grow from the Wheeler-DeWitt equation and relational quantum gravity, and the various proposals for quantum gravity that take the absence of time seriously, causality faces challenges that go deeper still. Some proposals in quantum gravity replace causal sequences with what are called causal sets, discrete, partially ordered structures where some events are related by a primitive ordering relation and others simply are not. A causal set is not a sequence of moments laid out along a timeline. It is a collection of discrete elements with some of them standing in a relation that can loosely be described as before and after, but where that relation is not derived from time. It is more fundamental than time, and time is reconstructed from it in appropriate limits, the way you can reconstruct the height of a mountain from a topographic map without the map itself having any height. The causal set program is one of the more mathematically elegant approaches to quantum gravity, and its central insight is that the ordering relation between events, the primitive notion of which comes before which, might be more fundamental than the continuous time coordinate of general relativity. Time, in this picture, is what you get when you have a causal set large enough and dense enough to approximate a smooth continuum. At the Planck scale, below the resolution of any instrument we currently have or can currently conceive, there is no smooth time. There is only the discrete partial ordering, the raw causal structure, without the continuous parameter we call time draped over it. Other proposals are more radical still. Some approaches to quantum gravity suggest that causality itself is emergent, that at the Planck scale, there are not even discrete causal relations between events. There are only correlations. Correlations without direction, without ordering, without any primitive notion of before and after. The appearance of causal structure, the sense that the world has a directional grain, that effects follow causes and not the other way around, emerges statistically from the correlations in the same way that the arrow of time emerges statistically from the entropy gradient. Neither is fundamental. Both are patterns that appear when you zoom out far enough from the timeless, causeless, correlation-defined foundation of reality. This is genuinely difficult to absorb, and it is worth being honest about that difficulty rather than smoothing it over. We're not talking about a minor revision to the ontology of physics. We're talking about the possibility that the most basic explanatory structure in all of science, a causes B, the past produces the present, earlier events are responsible for later events, is not a feature of fundamental reality, but an emergent pattern generated by something that has no causality in it at all. The same way that temperature emerges from particles that individually have no temperature, and the same way that time emerges from a quantum state that has no time variable, causality may emerge from a substrate that has no directional causal structure whatsoever. Physics as a predictive enterprise still works in all of these frameworks, and this is important to emphasize because the natural response to learning that causality might be emergent is to worry that science itself is undermined. It is not. You can still calculate probabilities of outcomes. You can still design experiments and predict their results with extraordinary precision. You can still build bridges and develop medicines and send spacecraft to the outer planets. The correlation structure of the universe, whatever its ultimate ontology, produces reliable regularities that science can map and exploit without needing to resolve the question of whether those regularities are underwritten by genuine causation or by something more primitive that merely generates the appearance of it. The predictive power of physics does not depend on causality being fundamental. It depends on correlations being stable, and stable correlations are exactly what the timeless frameworks provide. But the intuitive story does not survive. The sense that the universe is being generated moment by moment, cause by cause, with the present producing the future the way a fire produces heat. That story, which is so deeply embedded in how human beings think and speak and explain that most of us have never noticed it is a story, does not survive contact with these frameworks. The universe is not being generated. Nothing is producing anything. The generation is an experience, not a process. The fire is not making heat in a generative sense. The fire and the heat are correlated features of a static structure that contains both of them simultaneously, and the experience of one producing the other is what that correlation feels like from inside a brain that processes it sequentially. What is left, when causality is reconstructed rather than given, is something that functions like causality in every practical sense, something that supports prediction, explanation, and intervention just as reliably as the intuitive picture, but that sits on a foundation which is not itself causal, a foundation that is, at its deepest level, a pattern of correlations in a timeless structure, generating the experience of a universe that moves, changes, causes, and becomes, generating it so completely and so consistently that the generation feels like the most obvious thing in the world, until you look at the equation and find that the generation was never there. Part 18. The free will problem. The block universe, if taken literally and consistently, is deterministic in a very specific and absolute sense. Not deterministic in the way that classical Newtonian mechanics was deterministic, where the future is fixed in principle but could in theory be changed if the initial conditions were different, but deterministic in a deeper and more final way. Every choice you will ever make, every thought you will ever have, every action you will ever take is already a feature of the static four-dimensional structure. Not fixed in the sense of being locked in place by a chain of prior causes stretching back to the Big Bang, though that too, but fixed in the more radical sense of simply existing already, as part of the complete and unchanging geometry of space-time. The choice you will make tomorrow morning about what to have for breakfast is not going to happen. It has happened, in the only sense that matters in the block universe. It exists as a feature of the structure, located at the space-time coordinates corresponding to tomorrow morning, as real and as fixed as the chair you're sitting in right now. This is where the physics becomes personal, in a way that is difficult to maintain at a comfortable intellectual distance. You can engage with the Wheeler-DeWitt equation as an interesting mathematical curiosity. You can find the block universe philosophically provocative without feeling personally implicated. But the moment you follow the logic to its conclusion about choice, about the decisions that feel most genuinely yours, most genuinely open, most genuinely the product of your reasoning and your values and your effort, something shifts. The stakes become immediate. Because if the block universe is right, then every moment of genuine deliberation you have ever experienced, every time you weighed options and felt the weight of the decision and chose, was not a process that produced an outcome. It was a process that was itself an outcome, a feature of the block alongside the choice it appeared to be making, correlated with that choice not because the deliberation caused it, but because the deliberation and the choice are both just there, together, in the structure. You did not make those choices in a process of deliberation moving through time. The choices exist in the block alongside the deliberation, as correlated features of the same structure. The deliberation is real. The anguish of a difficult decision is real. The effort of reasoning carefully is real. None of that is dismissed or trivialized by the block universe picture. But real in this context means existing as a feature of the four-dimensional structure. It does not mean causally responsible for what came next. The deliberation and the choice are correlated the way the smoke and the fire are correlated in the block universe, not because one produced the other in a generative sequential sense, but because they are adjacent features of the same static geometry, and observers moving through that geometry in the time direction experience the correlation as production. Whether this means free will is an illusion is a question physics cannot answer, and it is worth being precise about why. The question of free will is not a physics question. It is a question about what free will means, about which of the many things we might want the phrase to refer to are actually present in the situation being described. If free will means the ability to have done otherwise given exactly the same prior state of the universe, then the block universe does eliminate it. because in the block universe there is no such thing as doing otherwise. The other options do not actualize. They exist perhaps as features of nearby possible block universes, but in this one, what happened is what happened, and what will happen is what will happen, and there is no branching point where the structure could have gone differently. In that sense, yes, the block universe is incompatible with the most naive version of libertarian free will. But if free will means something more modest, the ability to act in accordance with your own reasoning and values, to be the kind of system whose behaviour is responsive to evidence and argument and deliberation, to be the proximate cause of your actions in a way that distinguishes you from someone who is coerced or manipulated, then the block universe does not obviously eliminate it. A configuration that deliberates and then acts in accordance with its deliberation has a meaningful relationship with its actions, even if that relationship is correlation rather than sequential causation. The deliberation matters, in the sense that configurations that deliberate are correlated with different outcomes than configurations that do not. The correlation is real. The responsiveness is real. What is absent is the metaphysical openness, the genuine branching of possibilities that some accounts of free will require. Whether that absence is a problem depends entirely on whether that openness was ever what you actually cared about when you valued free will. What physics can say, and this is perhaps the most clarifying thing it contributes to the debate, is that the experience of choice, the felt sense of genuine openness, of multiple futures being genuinely possible until the decision is made, is a feature of consciousness processing a particular slice of the block universe, not a feature of the universe itself generating multiple possibilities and collapsing to one. The universe does not deliberate. It does not entertain options. It does not stand at a fork in the road and choose a direction. It is the road, all of it, in every direction, simultaneously present in a static structure that contains the fork and both paths and your footsteps on one of them, and the untaken path lying quiet beside it. You deliberate because deliberating is what configurations like you are. You are a physical system of extraordinary complexity whose behaviour is shaped by information processing, by memory, by modelling of future states, by the evaluation of options against values and goals. That processing is real. It is physically happening, in the sense that it is a feature of the block. It is causally relevant, in the reconstructed sense that correlations between deliberating configurations and specific outcomes are stable and lawful. But it is not opening the future. The future is not open. The future is already there, in the block, waiting not to happen but simply existing, the way the last page of a book exists while you are still reading the first. And the strangest part, the part that physics notes without being able to explain, is that knowing this changes nothing about the experience. You will still deliberate. You will still feel the weight of decisions. You will still experience the next moment as genuinely undetermined, as something about to happen rather than something already fixed. The block universe can tell you that the experience is a construction. It cannot tell you how to stop having it. And that gap between what the physics says and what the experience insists is the quietest and most persistent mystery in all of this. Part 19, the radical possibility. The most speculative but arguably the most promising direction in current quantum gravity research connects the disappearance of time to a completely different concept, quantum entanglement. And to appreciate why this connection is so striking, it helps to start with what entanglement actually is, because the popular version of the story tends to leave out the part that makes it relevant here. Entanglement is the phenomenon where two quantum particles become correlated in such a way that measuring one instantly affects what you find when you measure the other, regardless of the distance between them. Not effects in the sense of sending a signal, not effects in the sense of one particle nudging the other through some invisible medium. Affects in the sense that the two particles share a single quantum state, a single mathematical description that cannot be factored into separate descriptions of each particle individually, and when you interact with one of them, the shared state updates in a way that is reflected in what you find when you interact with the other, no matter how far apart they are. Einstein famously called this spooky action at a distance and spent years trying to find a way around it, convinced that the apparent non-locality was a sign that quantum mechanics was incomplete rather than a feature of reality itself. He was wrong. Decades of increasingly precise experiments, culminating in the loophole-free Bell inequality tests of the 2010s, have confirmed beyond any reasonable doubt that entanglement is real, non-local, and not explainable by any theory that assigns definite local properties to particles before measurement. It is not spooky action at a distance. It is a fundamental feature of how quantum systems relate to each other. And it turns out that this feature, this deep, non-local, irreducible correlation between quantum systems, may be the thing from which time is made. The proposal that makes this precise is called the Page-Wouters mechanism, developed originally by physicists Don Page and William Wouters in the early 1980s, and refined and extended significantly over the subsequent decades, most recently by Ekaterina Moriva and collaborators at the Istituto Nazionale di Ricerca Meteorologica in Turin. The core idea is stated simply enough that it fits in a single sentence, though unpacking what it means takes considerably longer. Time is what entanglement looks like from the inside. Here is how it works. Take any quantum system, it could be a laboratory experiment or in principle the entire universe, and divide it into two parts. Call one part the clock and the other part the rest of the system, the universe subsystem. Now write down the global quantum state of the combined system. If you do this correctly, using the Wheeler-DeWitt equation as your guide, the global state is timeless. It has no time variable. It does not evolve. It is a static quantum state that describes the total system, clock plus universe, without any reference to time. From the outside, if there were an outside, nothing is happening. The total system simply is, in the same frozen, static way that the Wheeler-DeWitt equation describes the universe as a whole. But the clock and the universe subsystem are entangled. Their quantum states are correlated in the precise technical sense. The state of the universe subsystem is not independent of the state of the clock subsystem. They share a quantum description that links them, and now ask a different question. Instead of asking about the global state of the total system, ask a conditional question. What does the universe subsystem look like when the clock is in a particular state? What is the state of the universe given that the clock reads a specific value? When you do this calculation carefully, something remarkable emerges. The universe appears to evolve. The state of the universe subsystem, conditional on the clock reading one value, is different from the state of the universe, subsystem conditional on the clock reading another value. As you condition on successive clock states, as you ask what the universe looks like at clock time 1, clock time 2, clock time 3, the universe subsystem changes. It looks, from the inside, like it is moving through time. It looks like physics is happening, like states are following states, like the universe is becoming rather than simply being, and the total quantum state, all the while, has not changed at all. From the outside, from the perspective of the global description, nothing happened. The timeless quantum state sat there, static, complete, unchanged. But from the inside, from the perspective of an observer who is part of the universe subsystem and uses the clock subsystem as a reference, time passed. Events occurred. The universe evolved. The experience of temporal progression was generated entirely by the entanglement correlations between the two subsystems, without any time variable anywhere in the fundamental description. Time, in this framework, is the apparent evolution that emerges when one entangled subsystem is used as a reference for another. The universe has no time from the outside, and there is no outside, which is precisely the point, but it has time from the inside, because different parts of it are entangled with other parts, and those entanglement correlations produce, for any observer embedded within the system and using part of the system as a clock, a complete and consistent experience of temporal change. You experience time because your brain is part of the universe and is entangled with the rest of it. Every moment of felt duration, every experience of one thing following another, every sensation of being here now and not there then, all of it is the subjective experience of entanglement correlations being processed by a sufficiently complex physical system. Time is not something the universe moves through. Time is something the universe generates internally, through the correlations between its parts, for observers who are themselves part of those correlations. This is not a metaphor. It is not an analogy being stretched for explanatory purposes. Moreva and collaborators published an experimental test of this idea in 2013, using pairs of photons prepared in entangled states, and found results that are consistent with the Page-Wouters mechanism, with time emerging from entanglement rather than being a fundamental external parameter built into the equations. An observer who was external to the photon system and could measure its global state found no evolution. The global state appeared static as the mechanism predicts. An observer who was internal to the system, using one photon as a clock and measuring the other relative to it, found apparent evolution. The system appeared to change in time, as the mechanism also predicts. The same physical system looked timeless from outside and temporal from inside, exactly as the Page-Wouters mechanism says it should. It was a small-scale quantum optics experiment, not a cosmological demonstration. Two photons are not the universe, and confirming the Page-Wouters mechanism for a pair of photons does not prove that the mechanism is responsible for the time you experience right now. But it was a genuine experimental probe of the central question: can time emerge from a timeless quantum system through entanglement alone, without any time variable in the fundamental description? And the answer the experiment returned was yes. In principle, in a laboratory, with real photons and real measurements, yes. If this is right, and it is far from established, it has contested assumptions, it has competing interpretations, and the gap between a two-photon demonstration and a cosmological claim is vast. The implications are transformative in a way that is difficult to overstate. The universe is not a system evolving through time. It is an information structure in which different subsystems are mutually entangled, and the entanglement correlations between them produce, for observers embedded inside the system, the experience of time passing. Reality is not temporal at its foundation. Reality is informational, and time is a way that information feels from the inside, the experiential signature of being a complex entangled subsystem, processing its correlations with the rest of a timeless quantum state. This connects everything. The Wheeler-DeWitt equation has no time variable because the global quantum state it describes is genuinely timeless, and that is not a problem to be solved, but a feature to be explained by the emergence of time through entanglement. The quantum clock experiments reveal that reading time costs more energy than keeping it, because extracting temporal information from a quantum system requires physically interacting with the entanglement correlations that constitute time at that scale, and that interaction is not free. The block universe follows naturally from a timeless informational structure in which all configurations are encoded simultaneously in the quantum state. The emergent time program is the large-scale limit of the Page-Wouters mechanism, the regime where the entanglement correlations are so numerous and so consistent that they produce a smooth, reliable, classical-looking arrow of time. The relational view of time that Rovelli defends is precisely the view you would expect if time is generated by correlations between subsystems rather than flowing independently of them. The universe did not begin in time. The universe began as a pattern of quantum correlations, an initial entanglement structure that generates from the inside for observers embedded in it the experience of having begun in time. The Big Bang is not an event that happened in the past. It is a feature of the correlation structure that observers like us, located in a particular region of the entanglement network, read as the past when we process the information encoded in our region of the quantum state. The past is not where we came from. The past is the low entanglement direction in the information structure we are part of. Whether the Page-Wouters mechanism is the final answer, or a piece of the answer, or a stepping stone towards something we cannot yet see, it represents the most radical reconceptualization of reality that physics has seriously entertained since Einstein demonstrated that space and time were aspects of a single geometric structure. And unlike many of the speculative ideas that circulate at the frontier of theoretical physics, this one is not waiting for a particle accelerator that does not yet exist, or a telescope that cannot yet be built. It is connected to real experiments, real mathematics, real predictions that the current and next generation of quantum information and quantum gravity research can test, refine, and potentially confirm. Time may be what entanglement looks like from the inside, and you, reading this, feeling the seconds pass, certain that now is now and then was then, may be what entanglement looks like when it becomes complex enough to wonder about itself. Part 20. The final realization. Come back to where this started, an equation with no time variable, a universe described as static, and you, here, 1 second after the last, as certain of this moment as you have ever been certain of anything. The tension between those two things, between the physics and the experience, is the engine that has driven everything in this exploration. It is not a tension that resolves cleanly. It is not a puzzle with a solution waiting at the bottom of a calculation, a mystery that will dissolve once someone writes the right equation or runs the right experiment. It is a tension that deepens the further you follow it, that grows more precise and more uncomfortable the more carefully you look. And now, after travelling through the Wheeler-DeWitt equation, an emergent time and the block universe and quantum clock experiments, an entanglement-based time and the relational universe, it is time to decide what to make of it. Or rather, to sit honestly with the fact that there is not yet a clean answer, and that the absence of a clean answer is itself the most important thing to take away. Physics does not always give you closure. Sometimes the most honest thing it can do is sharpen the question until it cuts. Here is what the physics is saying, gathered from its disparate sources into a single current. Time, at the most fundamental level we can currently access mathematically, is absent from the description of reality. This is not a provisional gap waiting to be filled by the next generation of physicists or the next generation of particle accelerators. It is a feature of the deepest equations we have, arising from the collision of the two best theories in the history of physics, general relativity and quantum mechanics, when you attempt to combine them into a single description of the universe as a whole. When you try to describe the universe as a complete quantum system, time drops out. Not as an oversight, not as an approximation made for computational convenience, not as a placeholder standing in for something more fundamental that will be added later, as a mathematical result. The equation is solved and time is not in the solution, the same way 2 + 2 is solved and 5 is not in the answer. The absence is not a whole, it is a finding. Time at the scale of everyday experience is real in the sense that emergent phenomena are real. Temperature is real, the pressure of a gas is real, the surface tension of water is real, rush hour is real, your experience of time passing is real. But real in this sense carries a specific and limited meaning, a reliable, consistent, measurably accurate description of a large-scale pattern arising from a more fundamental substrate that does not itself contain the pattern. Temperature is real but does not appear in the equations governing individual particles. Pressure is real but does not appear in the quantum mechanical description of a single molecule. Time is real but does not appear in the Wheeler-DeWitt equation for the universe. The reality of emergent phenomena is genuine. It is not a polite fiction or a useful approximation that secretly means false. But it is not the same kind of reality as the substrate from which the emergence occurs. And that distinction between emergent reality and fundamental reality is the distinction that everything in this story has been circling. Time, at the experimental frontier of quantum metrology, is showing signs of being not just emergent but expensive. Reading time at quantum scales costs more energy than keeping time. The act of measuring time disturbs the thing being measured more profoundly than any ordinary quantum measurement. Time is not passive at the quantum level. It does not sit there quietly, available for inspection at no cost, the way a label sits on a jar. It is something that physical interactions produce at a cost through the exchange of information between systems. Every determination of duration at the quantum scale requires an investment of energy that exceeds the energy involved in the timekeeping process itself, which suggests that time is not a background feature of reality that physical processes happen against. It is something that physical processes generate actively through interaction, and at the smallest scales the generation is harder than the thing being generated, and time, in the most speculative but increasingly testable frameworks of quantum gravity, may be what entanglement looks like from the inside. Not a river flowing from the past to the future, carrying events downstream on its current. Not a dimension laid alongside space, extending the three directions of position into a four-dimensional geometry. Not an external background against which the drama of physics plays out, unchanged by the drama itself. A description of correlations between the parts of a quantum system that has no time at its foundations but generates, for observers embedded within it, processing those correlations through the machinery of perception and memory and anticipation, the complete and vivid and utterly convincing experience of temporal existence. The page-routers mechanism says that a timeless global quantum state, internally divided into entangled subsystems, looks like time from the inside. The experimental confirmation with entangled photons says the mechanism works in the laboratory. The extrapolation to cosmological scales says it may work for the universe. And if it does, then every second you have ever experienced was not a feature of the universe, but a product of your relationship with it. What do you do with this? One honest response is to continue living as though time is real, because at the scales that matter for human life, for relationships, for work, for planning, for memory, for everything that constitutes a human existence, the emergent description is so accurate and so reliable that there is no practical alternative and no practical reason to seek one. Time works, calendars work, clocks work, history works, memory works, physics works, in the sense of producing predictions that match experiments to extraordinary precision using time as a parameter. The emergent description is not false. It is not a lie the universe is telling you. It is a valid and accurate description of a large-scale pattern arising from a timeless foundation, and the fact that the pattern emerges from something that does not itself contain time does not make the pattern less useful, less consistent, or less true at the level it operates at. You do not need to know that temperature is emergent to use a thermometer correctly. You do not need to know that time may be emergent to make it to your appointments. But another honest response, a harder one, less comfortable, more demanding, is to sit with what it means that the experience you take to be most fundamental, most immediate, most undeniably real, is not in the basic equations. To notice that every anchor you have ever had in your sense of being a self in a world, the certainty of being here, now, in this moment, with the past behind you and the future ahead, with the present as the one real thing in a universe of things that either no longer exist or do not yet exist, is a construction, not a deception, not a mistake, not something to be corrected or escaped or mourned, but a construction, a pattern generated by a timeless structure and interpreted by a brain that evolved to navigate a world at scales where the pattern holds so reliably that questioning it never became necessary for survival. To notice that beneath that construction, if the physics is pointing in the right direction, there is something quieter and stranger, and in some sense older than time, a static quantum structure in which all of history and all of what comes after are equally present, equally encoded, equally real, separated not by the flow of time but by the geometry of entanglement correlations that you will never directly perceive and that your experience will never directly reveal. The universe is not moving. It is not becoming. It does not travel from the Big Bang toward the heat death the way a story travels from its opening line to its last page, with each sentence producing the next, with the ending not yet written while the beginning is being read. It contains all of that. The Big Bang and the first stars and the emergence of life and every civilization and every moment of every conscious experience, and you, here, in this moment, with this exact thought crossing your mind, all of it simultaneously present, all of it equally real, all of it encoded in a structure whose fundamental description contains no variable called time, and no process called change, and no direction called forward. And the most unsettling version of that idea, the version that earns this the title of the most dangerous idea in physics, is not the static universe. The static universe is strange, but it is at least impersonal. It does not implicate you specifically. The block universe is philosophically vertiginous, but it is at least a complete picture, everything existing, nothing lost. Not even the Wheeler-DeWitt equation, sitting there with its missing time variable, is the most unsettling part. The most unsettling version is the one suggested by the page routers mechanism and the quantum clock experiments and the informational view of physics working together toward a single implication. That time may not exist except as an experience generated by observers embedded in a timeless structure. That without observation, without the processing of entanglement correlations by physical systems complex enough to perform that processing, time would not be real, even as an emergent phenomenon. That the universe does not just contain no time at its foundation, it may generate time only when something inside it becomes sufficiently complex to experience it. Time is not waiting to be experienced. Time is produced by the experiencing, which means time is not something the universe is made of. Time is something the universe makes by making you. The most dangerous idea in physics right now is not about black holes or parallel universes or the end of space or the collapse of matter into singularities. It is closer than any of those things. It is happening right now, in the only place it can happen. It is that the second that just passed, the one between when you started this sentence and when you finished it, that irreducibly felt, undeniably real, absolutely certain unit of your existence, may only have happened because you were here to experience it. That without the observer, without the brain running its entanglement-based clock, without the information processing that constructs the experience of now from the correlations available to it, the universe has no present moment at all. Not a present moment that nobody is observing. Not a present moment happening in the dark. No present moment. The now is not a location in the universe that you happen to be visiting. The now is what your existence does to a timeless structure. Not because the present is special, but because the present is you. And somewhere in the foundations of physics, in the equations that have no time variable, and the quantum states that have no direction, and the entanglement correlations that have no arrow, something that has no name yet is waiting for us to understand what that means. We are only just beginning.